So welcome to lecture 18 of E720. So in the last lecture we introduced RSA, the public key encryption scheme named after Rivest, Shamir and Adelman. So I said that we'll do a numerical example in this lecture, so let's do that one. So recall that you had a algorithm called Gen RSA that which would give you it's a PPT algorithm, probabilistic polynomial time algorithm, which would take a security parameter as input and output three things, a modulus n and two integers, positive integers e and t greater than 1. The modulus is the product of two n-bit primes. So it also outputs integers e and t which are greater than 1, satisfying t times t equals 1 modulo phi of. So this was Gen RSA. So given this, so the way it would work is that suppose Alice wants to send a message to Bob. Bob would run Gen RSA to generate NED. And then Bob is going to publish N and E as his public key. So he'll tell Alice, my public key is, so maybe the first step would be that he would actually send Alice N and E. So, and then Alice will send Bob some C. Let's see the ciphertext, where the way C is going to be m to the e mod n for some message in Zn star. And as I said before, the message which Alice wants to send may be some arbitrary bit string, but here m has to be an element in Zn star, so that mapping has to be done by Alice. So let's say that is not a hard problem, so we'll not go into the details of that, how the mapping of arbitrary bit strings to some messages and some elements in Zn star is done. Let's say that is given to us, some encoding method. We can think of, if n is very large, we can think of this some power of 2 to if n is greater than or Zn star, phi of n is greater than some power of 2, then let's say it's greater than 2 power 1024 or some large number like that, then all 1024 bit strings could be mapped to elements in this M. So given this, the mapping is done and ciphertext is available to Bob. The way Bob will decode is M hat. The estimate of the message is going to be C to the D mod n, where D is the private key which Bob did not send to Alice, and so the eavesdropper also does not see that. So an eavesdropper only sees N and E, the public key of Bob. Okay. So the numerical example will be as follows. Suppose NED is suppose Gen RSA gives NED equals 391, 3 and 235. This is a toy example because we want n to be so large that factoring it should be difficult. Otherwise, from n and e, we can calculate d easily. So here n is 391. It's a product of 17 and 23. So phi of n is, recall that if n is p times q, phi of n is p minus 1 times q minus 1. So it's 16 times 22. It's 352. And also the d has to be the multiplicative inverse of e modulo phi of n. So here it turns out that d, this is 235 is d, e is 3. So 3 times 235 turns out to be mod 1 mod 352. You can check that. So 3 times 235 is 705 and 352 times 2 is 704. So this turns out to be 1 mod 352. So suppose you have some message now. Suppose m is 158, which is in Z 391 star. Then the ciphertext would be C is 158Q mod 391, which turns out to be 295. You can check that. And then the decryption of M of C is M hat, which is C to the D mod n, which is 295 raised to 235, sorry, mod 391, and you would get back 158. Okay. So RSA depends upon this Gen RSA algorithm, which on input a security parameter, it has to generate this modulus n, which is a product of two n-bit primes. So the question is that how do you generate these primes? So it can't be that you just generate these primes once and every user cannot have the same primes. Every user, in our example of Alice and Bob, Bob had a modulus, which is a product of two primes. Now Alice cannot have the same modulus, so Alice has to have her own modulus. So every receiver of information has to have their own unique modulus. So these P and Q have to be generated differently for every user. So the question becomes how to randomly generate n-bit primes. Because we want the procedure to be unpredictable. Because if I know somebody's prime generation algorithm, then I'll know what primes they have, even if they don't tell me what they are and reveal only the modulus n. So somehow there should be some randomness involved. So the answer turns out, or the way to do it is to you generate a random n-bit prime and check whether it is prime. You generate a random n-bit odd integer and check whether it is prime. So what you need to do is generate a random n-bit odd integer and check whether it is a prime. And if it is not a prime, you generate another odd n-bit integer and keep trying. So this is called primality testing, which is the next topic. It is the methods which are used to check whether an integer is a prime or not. Even integers other than 2 are all not prime. So we'll basically be mainly concerned with odd integers. And uh, so why should this method work? So I just keep generating random n-bit odd integers and checking whether they're prime. So there is a postulate which says that, it's called Bertrand's postulate. For any n greater than 1, the fraction of n-bit integers that are primes is at least one over 3n. So if you look at space of all n-bit integers, this postulate claims that at least 1 by 3n of them are primes. But you might say that as n becomes larger, this fraction seems to be becoming smaller and smaller. That is true, but we have a larger space of integers to choose from also. So suppose we were to choose, so if we choose 3n square random n-bit integers, so 3n square is still a polynomial in n. So you choose a polynomial number of integers. The probability that a prime is chosen is at least, or is at most 1 minus 1 over, oh sorry, I should say the prime, I should say the probability the prime is not chosen is at most 1 minus 1 by 3n raised to 3n square. So this is the probability. So at least 1 over 3 of n of the n-bit integers are prime. So 1 minus the probability that is one of them, if one choice is not a prime, is 1 minus 1 by 3n. And if the choices are if you're choosing them like independently of each other and they're all distinct, so then you have this probability here. And this I can write as 1 minus 1 by 3n raised to 3n whole raised to n. So there is an identity which says that 1 minus 1 by x raised to x is less than or equal to e inverse for x greater than or equal to 1. So this is, let me put that, for x greater than or equal to 1, 1 minus 1 by x raised to x is less than or equal to e inverse. So this is less than or equal to e to the e inverse raised to n, which is e minus n. So if we choose 3n square random n-bit integers, the probability that a prime is not chosen is exponentially small. So at least one of them must be prime. So all we need now is a way to distinguish between integers which are prime and which are not prime. So after this polynomial choice, a polynomially sized set, if I had a reliable way of telling which is a prime and which is not a prime, in a polynomial, in an algorithm which takes polynomial time, then I will definitely end up with a integer which is prime, because the probability that no prime is chosen is exponentially small in n. Okay, so how can I test whether an integer is prime or not? Factorization, as I argued last time, it's like not that is, if trial division is not uh, a feasible strategy, trial division is that given an integer capital N, you just try dividing it by all integers from 2 to square root of n. It's not a feasible method for primality testing, mainly because it is exponential in the bit length of the integer you want to check. So it is order 2 raised to n by 2, we said polylog. So the last lecture we said that the running time of trial division is if n capital N is the integer you want to check, uh, that is, you want to check whether capital N is a prime or not, then the running time of trial division is worst case ordered exponential in the bit length of n, where this double bar means the number of bits in this integer, number of bits which are needed to express this integer in binary form. So this is not a feasible strategy, so we need some other method to uh, check whether capital N is a prime or not. So what other methods do we have to check whether an integer is a prime or not? So recall Fermat's little theorem, which says that if p is a prime and a is any integer not divisible by p, then a raised to p minus 1 equals 1 mod. So how can I use such a theorem? So suppose we are given n, and we want to check, and n is a large integer, n greater than 1, but n is a large integer, and it's going to be odd because even integers other than 2 are all not prime. We want to check if n is a prime or not. Okay. So how about this strategy? So I choose a in randomly. So if I choose some integer a in the range 1 to n minus 1 randomly, now all the integers in this are not divisible by n because they're strictly less than n. Okay. So if n were a prime, then according to Fermat's little theorem, a raised to n minus 1 should be equal to 1 mod p. So calculate, check if a raised to n minus 1 mod n is equal to 1. So if n were a prime, this will always be a raised to n minus 1 mod n will always be equal to 1 for a in this range, because it satisfies the hypothesis of the of Fermat's little theorem. We have, instead of p, we have n here, and a in this range is not divisible by n. Okay. So when will, or for which values of a, so if n is a prime, this will always be equal to 1. But suppose n is not a prime, suppose n is composite, then for which values of a will we get 1, and for which values of a will we get something which is not equal to 1. So suppose n is composite. Let's consider two cases. So the case 1 is that A is not in Zn star. So which means that, what does it mean? A is not in Zn star. A is already in this range 1 to n minus 1, which this implies that the GCD of A and n is not equal to 1, right? Because they're not relatively prime. Now this already shows that n is not a prime, because you have some integer in this range which has a greatest common divisor with n which is not 1. And if n were a prime, this would not be true. For all integers in this range, you would have this. Okay. So if A is in Zn star, uh, A raised to n minus 1 will not be equal to 1 mod. Why is that? Because if the GCD of A and n is not equal to 1, we claim that the GCD of A raised to n minus 1 and n should also not be equal to 1. Because so the claim is that if GCD of A and n is not equal to 1, then GCD of A raised to n minus 1 and n is also not equal to 1. Because you have a divisor between A and n that which is not equal to 1. Now that divisor will be common between A raised to n minus 1 and n as well, because uh, that divisor of A and n will also divide A raised to n minus 1 and n. So this is true, which means that this cannot be equal to 1. Why is that? So if A raised to n minus 1 equals mod 1 mod n, then you can write A raised to n minus 1 as 1 plus kn. A raised to n minus 1, I can write it as 1 plus kn for some integer k, which implies 1 can be written as an integer linear combination of A raised to n minus 1 and n. And we know that the GCD is the smallest positive integer, which can be written as an integer linear combination of the two integers whose GCD we have taken. So if A is not in Zn star, A raised to n minus 1 will not be equal to 1 mod n. So what was the argument? We already know the GCD of A and n is not equal to 1. If this GCD is not equal to 1, then the GCD of A raised to n minus 1 and n should also not be equal to 1, because this GCD will divide this GCD here. So we are arguing by contradiction. If this were not true, that is, if A raised to n minus 1 were in fact equal to 1 mod n, then A raised to n minus 1 is 1 plus some integer multiple of n. That means 1 can be written as a integer linear combination of A raised to n minus 1 and n. So this implies that, and 1 is the smallest positive integer, so which implies GCD A raised to n minus 1 and n is 1. This is a contradiction. Which contradicts this? So what was our strategy? We said that so we're given an integer n. The strategy we're going to use is we'll just choose some random integer from 1 to n minus 1 and we calculate this A raised to n minus 1 mod n and check whether it is equal to 1. And we said we'll look at two cases, where for the case when n is composite, because if n is prime, then this will always be 1. So if n is composite, we are trying to see if this strategy will give us what we want. Can we build it into a primality testing method? So for the case when A is not in Zn star, it will tell us that n is not a prime, because A raised to n minus 1, we argued just now, is not equal to 1 mod n. And so what if A is in Zn star, because it turns out that integers which are not in Zn star are very rare. So let me demonstrate that. So it turns out that for the cases we are interested in, um, integers not in Zn star are rare. Okay, let me quantify that. Suppose n is composite where n is p times q for p greater than 1 and q greater than 1. So some odd primes, let's say. Then what is the size of Zn star? So the size of Zn star, the number of elements in Zn star is by definition the Euler phi function evaluated at n, which is p times q, phi of p times q, which is p minus 1 into q minus 1. Okay, and so the the number of integers. So if I choose a in this range here, we choose an integer from 1 to n minus 1 randomly. So this is so how many of those will be in Zn star and how many of them will not be in Zn star? So we said that the integers not in Zn star are rare. So Zn star, a fraction of a's in Zn star is going to be this size divided by n minus 1. This uh, p minus 1, just say that in general it is phi of n by n minus 1. So if you have n which is large, because for small n anyway we don't need to do primality testing. So this is approximately phi of n by n. So I'm just replacing the n minus 1 by n. So this will be p minus 1 into q minus 1 for the special case of n equals pq. This, which is 1 minus 1 by p times 1 minus 1 by q. So if p and q are large factors of n, then if p and q are large, then this 1 by p will be very small and 1 by q will be very small. So this will be very close to 1. So most of the integers in this range will be in Zn star. So it's very rare to find integers which are not in Zn star. So in general, if you look at n as a product of a composite n, which is a product of some distinct primes. So if in general for n which is p1 raised to e1, p2 raised to e2 up to some p k raised to ek, where p1, p2, pk are distinct primes. So the fraction of you can say the probability that a random integer in one, two, up to n minus 1 is in Zn star is phi of n by n minus 1, which is approximately phi of n by n. And phi of n for a product of distinct primes like this is going to be p1 raised to e1 minus 1 into p1 minus 1. So you can check this because if you have a prime power, the number of the size of Zn star is going to be this. I think we proved this in a previous lecture. P2 minus 1, so on. Pk raised to ek minus 1 to pk minus 1 divided by p1 raised to e1, p2 raised to e2 up to pk raised to ek. So this is going to be 1 minus 1 by p1 times 1 minus 1 by p2 to 1 minus 1 by pk. So which means that this means that if your the factors of n are all very large primes, p1, p2, pk are all very large, then this will be very close to 1. If any of these are small primes, let's say p1 is 2, because if p1 is 2, then n is an even integer, there's nothing to check. It's already composite. If p1 is a small prime, then this fraction will be small, and so you'll be able to find integers in this range which are not in Zn star, and for those integers a raised to n minus 1 will not be equal to 1 mod n. Okay. But the integers n for which primality checking is hard is precisely those integers which are a product of very large primes, because if they were divisible by 7 or 11 or 13 or something like that, then it will be easy to check, because all primality checking algorithms initially check for small, they do in fact do trial division by small integers before they do any like fancy methods. So one thing before we look at the second case of A belonging to Zn star is that you might be wondering that if n is very, very large, then is a raised to n minus 1 mod n difficult to compute? Because what is n? N, let's say n is equal to pq, where p and q are n bit primes, like in the RSA case. Then we finally want to use these primality testing algorithms in the case where we want to generate such an n, where n is p times q. So we'll choose p and q randomly, which are n bit odd integers, and calculate n is equal to p times q. So n will be a 2n bit integer. So then if n is large, little n is large, like so if suppose n is a 1024 bit integer, then it is not difficult to compute. I have to do a raised to some very large exponent. So that means that in the exponent I have some 2 raised to 1024 some integer which is of that size. So you might be thinking that, yeah, is that difficult to do? So it turns out that you can do something called square and multiply algorithm. So this is not computationally intensive. So I'll give an example. So just for example, so what I want to illustrate is a square and multiply algorithm. So suppose n is 33, and we want to compute, let's make it 34, so 34, and we want to compute and a raised to n minus 1 mod n. So we want to compute a raised to 33. So it may seem that you have to do 32 multiplication. So a and then followed by a times a, then a times a, and so on. So this is this. but we in fact don't need to do 33 multiplications or 32 multiplications. What we can do is we can do like a square and multiply. So this is, so suppose I calculate, so from A I will calculate first, calculate um, A2, which is A square model. Okay. Then A3 is A2 square model, which is going to be A raised to 4 model. Now this is one multiplication. Sorry about that. So this first I calculate A2, which is A square model. That's one multiplication. Then I calculate A3, which is A2 square. So this is the second multiplication. So far we have done two multiplications. But A2 square is actually A raised to 4. Now A4 is going to be A3 square model, which is A raised to 8 model. Then so far we have done three multiplication: A square, A2 square, A3 square. Then A5 is going to be A4 square model, A to the 16. A6 is A5 square model, A raised to 32. Okay. So we wanted A raised to 33. So now we compute, finally just compute A raised to 33 model is going to be equal to A times A6 model. Okay. So this is a square and multiply. So you keep squaring, and then whenever you can multiply. So you wanted to compute A raised to 33. It looks like the brute force way would be to do 32 multiplications, A multiplied by A and then so on. But instead of that, if you keep squaring, you can compute it with far fewer multiplications. How many multiplications did we need? 1 here, 2, 3, 4, 5 and 6. So 6 multiplications instead of 32 multiplications. So you can, this method can be used to reduce the number of multiplications. So instead of doing order n multiplications where or order n minus 1 multiplications which is n minus 1 is in the exponent, you need to do only log of the exponent, log n of the order of that. So uh, so you don't need that many multiplications to calculate a raised to n minus 1. But anyway, let's come back to our primality testing. So our primality testing algorithm, so we had a case 1 where A was in some range. And case 1 was A was not in Zn star. But what happens if A is in Zn star? And why is this case more important? Because we argued that most of the integers in this range will fall in Zn star. The fraction of elements in this set which are not in Zn star is very small. So most of the elements will be in Zn star. So what happens to this? So now if we calculate A raised to n minus 1, what am I going to get? So if A belongs to Zn star, that means that GCD of A and n is 1. Okay. And then so this also implies that GCD of A raised to n minus 1 and n is also 1. Because if the common divisor between A and n is 1, and now if I just keep multiplying by only A, I'm not introducing any new divisors, so the GCD will have to remain 1. That is the intuitive way of arguing that. The without using any intuition, the way I would argue this is that so if GCD of A and n is 1, then there exist integers x and y such that this is true. integer linear combination of a and n is 1. So now I'll just raise it to the n minus 1 power. Okay. Why am I raising it to n minus 1 power? Because I want to say something about the GCD of a raised to n minus 1 and n. Now this, by the binomial expansion, this will say that the first, this term will be this x raised to n minus 1 times a raised to n minus 1, and then all the remaining terms will have n as a common factor. So you get this, where this is a integer. So I'm able to express 1 as an integer linear combination of a raised to n minus 1 and capital N, so which means that the GCD of a raised to n minus 1 and n must be 1. Okay. So if the GCD of a raised to n minus 1 and n is 1, so that means that there exists some other integers x prime y prime such that x prime a raised to n minus 1 plus y prime n is 1. So this implies that x prime a raised to n minus 1 equals 1 mod n. But we don't know what a raised to n minus 1 is. So all we get from this chain of reasoning is that x prime times a raised to n minus 1 is 1 mod n. Now, but a raised to n minus 1 mod n may or may not be equal to 1. So the second case where a belongs to Zn star, which is the majority of the a's in that range 1 to n minus 1, we don't know. That is, we don't get a conclusive answer that if I just compute a raised to n minus 1 mod n, it may or may not be equal to 1. So I can't use the same argument as before. But all is not lost. So we have this theorem which says that before I do the theorem, let me state a definition first. We just need some terminology. So we say that an integer a in Zn star is a witness for the compositeness of n if a raised to n minus 1 not equal to 1 mod. Okay. So you have a is in Zn star, so a is going to be from 1 to n minus 1. Now if a raised to n minus 1 is not equal to 1 mod n, we know that n is not a prime. So in fact, so this a is like it's testifying that n is not a prime. So it is a witness for the compositeness, the non-primeness of n. Okay. So now the theorem which I want to state is that if there exists a witness, so by definition, a witness must be in Zn star, because integers which are not in Zn star, integers in the range 1 to n minus 1 which are not in Zn star, anyway the a raised to n minus 1 will not be equal to 1 mod n. We already argued that. But the ambiguity was for the integers which do belong to Zn star, which are the majority of the integers. So when we say witness, we mean integers in Zn star. So if there exists a witness in Zn star, so here the Zn star is superfluous because by definition a witness is in Zn star, but I'll just state it here. that n is composite, then at least half the elements of Zn star are witnesses that n is composite. Okay. So if there exists, if there is at least one, then they have to exist many more. So why is this useful? So we have this set here 1 to n minus 1. So this is going to be Zn star union Zn star complement. Okay. Now if I choose some integer in this range and I raise it to, and I can compute a raised to n minus 1 mod n, a raised to n minus 1 mod n. If I choose some integer here, if that integer, if I'm lucky and if that integer falls in this, then that a raised to n minus 1 mod n will be not equal to 1. So if a belongs to Zn star complement, then I'll know immediately that n is not a prime. So if I'm lucky and it falls here. But in general, if it falls here, I did not get any information. So uh, if a raised to n minus 1 uh, uh, may or may not be equal to 1 if a falls in this, even if n is composite. But what this theorem is saying is that if there exists at least one a in Zn star such that a raised to n minus 1 is not equal to 1 mod n, then at least half the elements in this set will also give a raised to n minus 1 mod n not equal to 1. Now, as soon as I find an integer from in this range, which for which this inequality holds, I know that n is composite. Previously, we didn't know how many of the Zn stars will help us, how many of the elements in Zn star will help us. But this theorem says that if there is at least one element here for which this inequality holds, then at least half of the elements here will also have this inequality hold. So if I randomly choose from this, at least half of the elements in this are now going to be such that this inequality holds. So if I randomly choose from this with a probability at least half, I'll find an A for which this inequality holds and I know that n is composite. So if for A in Zn star, A raised to n minus 1 mod n will not be equal to 1 for at least half. So at least half of these have this inequality, all of these have this inequality. So which means that at least half of this, because this cannot uh, be, so however large this is, so let's say that these had x elements and these had n minus 1 minus x elements. So for how many elements of this set do we have this inequality? At least n minus 1 by minus x by 2 plus x. Okay, so that will be at least n minus 1 by 2 plus x by 2. So n minus 1 minus x by 2. So at least these many elements you have the inequality holds, plus all the elements in this you have the inequality holds. So at least for This is at least for these many elements, the inequality will hold. So and even if x is 0, um, this is at least n minus 1 by 2. So if I randomly choose from here the probability at least half, I'll find an A such that this inequality holds. So that is so that means that if I choose 100 times, then the probability that the inequality does not hold will be 1 over 2 raised to 100, which is a very small probability. So this theorem tells us that if we get lucky and there is a so let's go back to the theorem. So there exists a witness in Zn star such that n is composite. That is, what is the definition of witness again? If there exists at least one integer in Zn star A such that A raised to n minus 1 is not equal to 1 mod n, then at least half the elements in Zn star are witnesses. Which means that randomly choosing elements from this set and checking the inequality, each trial will succeed with, if n is composite, each trial will succeed with probability half, and it will fail with the probability which is bounded by half. So if I do 100 trials, then the probability that it will fail in all 100 is a negligible probability. It will be 1 over 2 raised to 100. So we can use this way to check the primality of n. Okay. So how do we prove the theorem? So what do we have? There exists an A and Zn star such that A raised to n minus 1 is not equal to 1 mod n. Okay. And we want to prove that at least half the elements in Zn star also satisfy this inequality. Okay. So we are actually going to use the Lagrange's theorem. So we're going to use group theory to prove this. So consider the subset H of Zn star which consists of elements B in Zn star satisfying B raised to n minus 1 equals 1 mod n. So what are these B's? These are non-witnesses. If B raised to n minus 1 was not equal to 1 mod n, this would be a witness for the compositeness of n. And we are saying that there is, so we are looking at non-witnesses. So first of all, the set is non-empty. So 1 belongs to H as 1 belongs to Zn star, and 1 raised to n minus 1 is 1 mod n. So one is so this set definitely contains at least one element. Now we are trying to see if what other properties this set has. So H is this elements of non-witnesses. So it turns out that H is a subgroup of Zn star. So what is H again? H is a set of elements for which B raised to n minus 1 equals a set of elements B in Zn star for which B raised to n minus 1 equals 1 mod n. So my claim is that H is a subgroup of Zn star, and it follows from this proposition here say by the following proposition. The proposition is this. It's 8.36. So let G be a finite group and H is a subgroup subset, and H is a subset of G. If H is non-empty, and closed under the operation for all A, B in H, we have A times B is in H, then H is a subgroup of G. Okay. So if you recall the definition of subgroup, we said that a subgroup is a non-empty subset of G which satisfies two things, which is should be closed under the operation, and for all little a in H, A inverse should also be in H. But here we are removing that inverse condition. We are just saying it just needs to be closed. The reason we can do that is because G is a finite group. So if G is a finite group and H is a subset of G, H is also a finite subset. H is a finite subset of G, which is closed under the operation. So if you now look at um, the proof, we just need to show that the inverse of A exists for any A in H, because the closure is already given to us. So if you consider the sequence A square, and so on, this sequence will be completely contained in H. So we'll look at actually we had a notation for this. We said angle bracket A cube, and so on. So if you look at this set generated by powers, consecutive powers of A, then this set is contained in H. Why is that? Because H is non-empty and it is closed under the operation. And then if you look at this set, so eventually this set would have to repeat. These sequence would have to repeat. And when the sequence repeats, we can show that so A raised to I is A raised to J for some J greater than I. So A raised to J minus I is equals 1. So we can argue that A times there exists a B for B in this. So we did a similar argument in the case when we discussed cyclic groups. So I will not repeat it because there are some cases when J is exactly equal to I plus 1 and when J is greater than I plus 1. There are these two cases you have to consider. So I'll skip that discussion for the sake of time. But you can argue that there exists element B which is also in this angle bracket A, and angle bracket A is a subset of H such that A times B equals the identity 1. So which means that B inverse exists in H and H is a subgroup. So this is the proposition. And where do we want to use this proposition? We want to use it to argue that this H, which is a set of elements satisfying this equality, B raised to n minus 4 equals 1 mod n, this is a subgroup. Because we can check that, so let's check that. So H in our case now is set of all B in Zn star such that B raised to n minus 1 equals 1 mod n. So for B1, B2 in H, We have b1 raised to n minus 1 equals 1 mod n, and b2 raised to n minus 1 equals 1 mod n. So b1, b2 raised to n minus 1 will be b1 raised to n minus 1 times b2 raised to n minus 1, which is 1 times 1 mod n. So this implies that b1, b2. Now, if b1 belongs to zn star and b2 belongs to zn star, b1, b2 mod n will also belong to zn star. And b1, b2 raised to n minus 1 is also 1. So this belongs to H. So H is closed under this operation. So G, by the proposition, H is a subset, a non-empty subset, because 1 belongs to H. It's a non-empty subset of Zn star. It is closed under the operation. So hence it's a subgroup. So which by the proposition, which is a subgroup. Okay. So how is this going to help us about prove the theorem, which says that if there is at least one witness that n is composite, at least then at least half the elements of Zn star are witnesses that n is composite. So so what does it say? H is the subgroup of is the subset of non-witnesses in Zn star. Now there exists an element which is a witness. So H is not equal to Zn star, as there exists a witness in Zn star for the compositeness of n. And H is a subgroup, which means that the order of H has to divide the order of Zn star. So by Lagrange's theorem, the order of H has to divide the order of Zn star. So that means that there is an integer k such that this is k times H for some k in Z. And what we know is that H is not equal to Zn star. So k cannot be equal to 1. Because if k is 1, then Zn star will be equal to H. H is not equal to Zn star because there is a H is a set of non-witnesses, and we said that there exists a witness for the compositeness of n. So which means that k should be greater than or equal to 2. So which means that Zn star, which is equal to k times the order of H, is greater than or equal to 2 times the order of H. This implies the order of H is less than or equal to Zn star, the order of Zn star by 2. Now H is the set of non-witnesses, which means the order of H complement, the set of witnesses in Zn star, is greater than or equal to Zn star by 2, the order of Zn star by 2. So which implies that there exist at least half the elements of Zn star are witnesses for the compositeness of H. percent of n, sorry. So this completes the proof of the theorem. So the theorem was, if there is at least one element, so if there exists an A such that if there exists an A in Zn star such that A raised to n minus 1 equals 1 mod n, sorry, I should say this, not equal to 1 mod n, that is if there is at least exists one witness for the compositeness of n in Zn star, then at least half of the elements of Zn star are witnesses, that they'll also satisfy this inequality. Okay, so that's great. I mean, that's a good test for primality if there exists an A in Zn star such that this is true. But it turns out that there exists integers n such that no such witness can be guaranteed. So what I mean is that, so there exist composite integers for which A raised to n minus 1 equals 1 mod n for all integers in Zn star. So these are called Carmichael numbers. And there exist infinitely many such Carmichael numbers. One example is the first Carmichael number is 561, which is composite. It's 3 times 11 times 17. So we cannot use a theorem for such numbers, because the theorem which said that if there exists at least one A in Zn star such that A raised to n minus 1 is not equal to 1 mod n, then at least half the elements in Zn star are witnesses. So I can randomly choose elements from 1 to n minus 1 and compute A raised to n minus 1. With the probability half, I'll get something which is not equal to 1. So I can keep trying it until I hit one integer there. But what if all the A's in Zn star will just give me 1? That is, the hypothesis of the theorem is not satisfied. Then I need a better test for primality. And that better test is going to be the Miller-Rabin test, which we'll discuss next.